I hope everybody is fine. And I wish that whatever I'm trying to deliver here, I wish it is of some help to the viewers who are viewing these lectures. And I hope if they find if they find something that's useful for them, they should like these videos, and I would expect them to share these videos so that other people can can have some benefit from these videos which I am making. So now moving on from here is that we would like to go in the domain of Bohr quantum theory of hydrogen atom, and precisely it was Bohr who applied this quantum theory of radiation to Rutherford's model. And as we know that that the model that was proposed for hydrogen atom, and that could explain successfully the origin of spectral lines in hydrogen atom, and also this model could be applied to some complex atoms. Now, what was Rutherford's model? Actually, Rutherford is he is known to be the father of nuclear physics because he discovered nucleus, and that contribution cannot have any equivalence in the domain of science. But but talking about the atomic model, this Rutherford could exactly discover precisely the existence of this, what we call as existence of nucleus inside an atom. And the main difficulty with Rutherford's atomic model was the explanation of stability of atom. He could not he could not explain why an atom is stable, and because if we consider that the electron if we consider that electron to be at rest, these electrons will be attracted by positively charged nucleus, and ultimately will fall into it. On the other hand, if we consider that they are in motion, the energy will be radiated, because from electromagnetic theory we understand that if we have accelerated charge, the accelerated charge produces electromagnetic waves. So so whether the electron is presumed to be at rest or it's presumed to be in motion, Rutherford's model could not explain the stability of this atom. And assuming that electron is in motion would certainly mean that its velocity changes as it moves around the nucleus. The change of velocity gives birth to acceleration. So once there is acceleration, there is radiation. So there must be radiation, and electron must lose energy continuously, and finally it should fall into the nucleus. So so Rutherford could not the Rutherford could not explain the stability of atom as a whole, and then thus the existence of atom will be destroyed completely if we assume that this electron is going to radiate. while it is moving in a circular orbit around the nucleus. So therefore, the modified model of stability of atom was given, which was also called as Bohr. It was called as Bohr Rutherford model. And in this case, what happened is that that what's assumed here is that any nucleus of atomic number Z will have positive charge. It will have positive charge Ze, where this E will refer to the charge, and Z will be the number of protons. Now, this nucleus is surrounded by Z electrons, which move in certain allowed circular orbits, where they do not radiate out energy. And these allowed orbits are called as stationary orbits. So allowed. So whatever is between these orbits is not allowed. And what we call them, we call them stationary orbits, right? And the equilibrium is achieved because of the Coulomb force between the electrons and the nucleus, the attraction between the two opposite charges, between electron and the nucleus, and this attraction basically provides the centripetal force. So what it provides is the centripetal force, of whose measure is mv squared by r, for maintaining the motion of the electron in the circular orbit. So 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 the modification, there is a need of modification of Rutherford's model, and the modification is introduced by virtue of these allowed circular orbits. And these circular orbits are special because what is presumed here is that electron does not radiate in these shells. And we can have this postulate for Bohr model that this centripetal force is equal to the electrostatic force between the nucleus, where we can have this Coulomb's law, where Z will be as atomic number E squared by R squared. So this was the first condition that was introduced for explaining the stability of an atom, where we have usual meanings that this m is basically mass of the electron. It is mass of electron. Now, this was the first condition. Let's go with the second condition. What's that? Now, the stationary orbits are those. So they are special orbits in the atom, and they are those in which the angular momentum of the moving electron, angular momentum of moving electron. What is angular momentum? That's L, that is mvr. This angular momentum of this electron is it's an integral multiple of, it is an integral multiple of h by 2 pi, where h is known as Planck's constant. So this is the next condition. So if I have to write down this in mathematical form, so mvr, that's the orbital angular momentum of electron that's revolving around this nucleus. It is the integral n. So that now this n can be 1, 2, 3, and so on and so forth. It's the integral multiple of h by 2 pi. So this is the second important condition for the postulate of Bohr's model of an atom, which further we will boil down to the hydrogen atom when we will use for Z equal to 1 in our analysis. Now, this n is an integral number, and this n is called as principal quantum number. This n, so this principal quantum number gives us the range of shells. So n equal to 1 will give me k, n equal to 2 will give me l, and so on and so forth. And this point is clear up to now that we have this quantum condition of angular momentum of electron equal to the integral multiple of h by 2 pi. So this is my condition number 2, and I will call this as condition number 1. I have written on left, I have written it on right, and now moving on, let's go with another important condition, and that is nucleus, stationary nucleus. So in this Bohr model, the nucleus is assumed to be much heavier, much heavier than electrons. So its motion may be ignored. So there is no motion assigned to the nucleus. Nucleus is assumed to be at rest with respect to the motion of electron, which is not true actually, because even though there is less motion, but nucleus has its own motion. But in this model, this nucleus is assumed to be at rest. And next important point is non-relativistic motion. Non-relativistic motion. So everybody understands what non-relativistic motion means. It means that the speed of the electrons that we have in circular orbits is very, very less than that of speed of light. So mass of electron is assumed to be constant. So there is no change in mass. Mass of electron is assumed to be constant, because electron has velocity very, very less than that of velocity of light. Then there is next important point, that is transition. Now this transition is magical in nature. And what this transition means, that the electron can jump from one stationary orbit to another stationary orbit. Okay? Now, if the jump is from the orbit of higher energy to the orbit of lower energy, the difference of energies is emitted as quantum of radiation. Quantum of radiation. So the energy that will be emitted as the electron jumps from higher energy level to the lower energy level, there will be emission of photons. There will be quantas that will have some specific energies. Now, if the jump is from lower orbit to the orbit of higher energy, the difference of these two energies required is absorption by the electron from some external agency. So it will absorb some energy and will be excited to the higher energy orbit. And the sixth point that I would like to talk about here is the frequency, frequency condition. Now, suppose, let us assume that this electron, if an electron jumps from one stationary orbit to another stationary orbit and has energy in the first orbit, say EI, and in the next orbit, say EF. So the electron is jumping from one stationary orbit to another stationary orbit. Okay, when there is a jump from one orbit to another orbit, the energies of electrons in initial and final states, we have EI and we have EF. The energy emitted or absorbed, the energy that will be emitted will be in case it comes from higher energy level to the lower energy level. Absorbed will be when electron will have some energy and go to the higher energy state. That is given by the photon, the energy of the photon. This difference in energy will result in emission or absorption of the photon. Now, this equation that we have here, this equation is called as Bohr's frequency condition. We call it Bohr frequency condition. So this is it. So these are the important postulates of Bohr's model of an atom. Precisely talking Bohr's model of a hydrogen atom. In the next video, we will go with the mathematical treatment of using these postulates that were proposed by Bohr to explain the stability of an atom.